Let's look at another application of right triangles. Here, a method that surveyors use to determine a small distance d between 2 points P and Q. And what we have are 2 points P and Q in the diagram, and this is our distance between P and Q. And that is called a subtense bar method. The subtense bar with length B is centered at Q and situated perpendicular to the line of sight between P and Q. Angle theta is measured, then the distance of D can be determined. So let's take a look at this diagram. Again, this is our distance that we want to measure, which is a distance between P and Q. They're going to call that distance D. And here what they do is they measure the angle generated by this subtense bar that has a point situated at the midpoint, actually a perpendicular bisector of that segment. So we have a right angle, and this point is the midpoint of the segment. Then what we do is we measure this angle theta between the two rays generating that angle to the endpoints of this segment. And from there, we then can identify this whole segment here as B, but we know that Q is the midpoint, so this is B over 2, and this is B over 2. As a matter of fact, when this actually occurs, this gives us a right triangle. So since I have theta, then this angle generated from our line is theta over 2. And this is theta over 2. So we have two congruent segments, two congruent angles, but the main key to this is that I have a right triangle. And that gives us another method of using right triangle trigonometry to find solutions of either theta, B, or actually D. Let's look at the next slide. Again, I have the diagram situated here, and I have two separate formulas that we can take a look at. Of course, if I look at the first formula with tangent, and I'm trying to identify or find theta, if I'm given B and D, all I need to do is substitute this into my formula, and I can find theta by using the calculator. But if I'm trying to find either B or D, I then can use one or the other of these two formulas. If I'm trying to find B, I would use tangent of theta. And in this case, again, remember that I am given a right triangle. And here, if I take tangent of theta over 2, which let's say it doesn't matter if it's the top triangle or the bottom one, but if I use the top one, this is theta over 2, that's my angle, and I use the definition of the opposite leg over the adjacent leg, well, if this is my angle, identified my opposite leg to be B over 2, so therefore that is the top of my fraction, and then my adjacent leg is D. Then to generate the value for B, I just simplify my equation. So here, what I'm going to do is take this top fraction, divide by D, which means this is B over 2 times multiply and find the reciprocal 1 over D. So that gives me this simplification of B over 2D. Then all I need to do is multiply both sides by 2D, and I get 2D tan theta over 2 to equal B. Similar circumstance over here, if I need to solve for D, is do the same thing. I will divide the top and bottom by B over 2, which actually means I'm going to take D times 2 over B. With this information, that will give me 2D over B. Then I can just multiply both sides by B and divide by 2, and I get my formula for D. Let's take a look at an example. Here they want us to calculate D when theta is 1 degree, 23 minutes, 12 seconds, and B is equal to 2. From the previous slide, we know the formula to find D is D equals B over 2 cotangent of theta over 2. Now, all we need to do is substitute in and make the calculation. B is equal to 2 over 2, cotangent of theta. Theta is given in degrees, minutes, and seconds. I need to calculate that into decimal degree, which I already have done. And that gives me a value of 1.386667. So I'm just going to substitute in 1.386667. I'm just going to estimate that because this ends up being 2/3 and put that over 2. Now, all I need to do is make a calculation using the calculator. I'm going to substitute in. 2 over 2 is 1, so I really don't need that, but I do need to recall that cotangent is the reciprocal of 1 over tan. So 1 divided by tangent of 1.386667 divided by 2. And I get 82.634107. Let's continue the example. Here, they tell us that angle theta usually cannot be measured more accurately than to the nearest 1 second. How much change would there be in the value of D if theta were measured 1 second larger? From the previous slide, I have brought over the calculator estimation, and here I have D equal to 82.634107. I also know that our previous degree was 1 degree, 23 minutes, and 12 seconds. And they want us to actually make this 1 second larger. So my new angle would be 1 degree, 23 minutes, and 13 seconds. And they wanted to know how much D would change. This is our previous one. All we need to do is do a similar calculation and find out what the difference is between my values of D. Again, to calculate D, I'm going to use the formula D equal to B over 2 cotangent of theta over 2. Also, I need to convert my degrees, minutes, seconds into decimal degree, which I have. So here, our value for a decimal degree is 1.38694444. Let's substitute in. My value for B, again, is still 2 over 2, cotangent of theta, which now with 1 second larger is going to be 1.38694444 divided by 2. All we need to do is substitute into the calculator. Again, cotangent is the reciprocal of 1 over tan, so that's 1 divided by tangent of 1.38694444 divided by 2. And I get my new value for D. Now all I need to do is find the difference between my two values, which here is 82.6341 minus 82.6176. So approximately we have a change of 0.0170 centimeters. And if you take a look at our situation, our first value of D was 82.63. Second D is 82.617. So as my angle increases, my D is going to shorten.